All right, so what I want you to do to start is to look at the beginning examples, and you are going to start with the warm up. So go ahead and review your ability to solve a system of equations. So that was section 3.1 and 3.2, where we were solving a system. And then the most recent section 3.3 is solving a system by graphing inequalities. All right, so just to go back and review, in number 1, I used substitution, where I set the y's equal to each other. So you had negative 3x plus 3 equals 2x minus 7. That allowed me to solve for x. Once you solve for x, you have to solve for y. You could solve for y by plugging x into either of the two y equals equations, and you got y equals 3. And number 2, I decided just to subtract the two equations. You could also have solved one equation for x and substituted that one in and solved for y. Either way, you get y equals 2 and x equals 1. And in number 4, I used elimination by multiplying both sides by a negative 2. And then in multiplying both sides by negative 2, I got y equals 1. And then once you had y equals, you could plug that back in. So you had 4x plus 3 equals 7. Subtracting 3 from both sides, you get 4x equals 4, or x equals 1. And then over in number 4, 5, and 6, you had to graph these and then get their solutions by shading. X greater than 5 is going to be a vertical line. So it's 1, 2, 3, 4, 5. Vertical line that is solid at x greater than or equal to 5. That line would have shading to the right. Because x values are greater. And then we also have our line, y greater than negative 3x plus 6. So your y-intercept is a positive 6. It goes down 3 and over 1. This line is dashed. So your solution, since that's y greater, will be all the points above the yellow and to the right of the red. So your overlap is going to occur in here. In number 5, the first equation, you need to solve for y. So we're going to divide everything by 3. That makes your y-intercept at 2/3. Our slope is down 5 over 3. So you're going to go from that point down 5, or rather up 5, and over 3, or down 5, and to the left 3. My line is dashed. And again, the y values are greater, so we would shade above. And then for the second part, you have y less than or equal to negative x plus 7. So your y-intercept is at positive 7. And your slope is negative 1. This line is solid. And it is shaded below. So everything below gets stopped by that red line. So it technically is in here, but the solution is that overlap of the yellow and red over here. So again, my solution comes from where they overlap. So if we were being tested or assessed on this, you need to make sure that that overlap is darker. Obviously, I still have the yellow over there. That's not wrong, but I need to know exactly where the darkest points are. Okay, and then in number 6, you could go about solving for y once again. You could also just plug in 0 and find your intercepts. So we could graph number 6 by finding our x and y intercepts. So if you plugged in x equals 0, we get y equals 2. If you plug in y equals 0, you get x equals negative 6. So those represent our intercepts for that graph. So you could plot the point negative 6, 0. You could plot the point 0, 2. And what that tells me is that my slope is up 3 and over 1. My line is dashed. The tricky part that when we don't solve for the y equals is knowing if my inequality stayed the same or if my inequality changed because I had to divide by a negative. Now in this case, there's no division by negative. It would be 3y less than negative x minus 6, and everything would divide by 3. So my y would be less than, therefore I would shade below. And then if we graph our second line, we have 2x minus 3y less than or equal to 4. So we would have negative 3y less than or equal to negative 2x plus 4. And then you have to divide by a negative 3. When you divide by that negative, it changes the direction of the inequality. So y is now greater than or equal to negative 2 divided by negative 3, which is positive 2/3 x minus 4/3. So once again, to plot an easier point, if I plugged in y equals 0, I get 2x less than or equal to 4, and I divide that by 2, and I get x equals 2. So this graph contains the point y equals 0, x equals 2. That is my x-intercept. So instead of starting my graph at my y-intercept, that is a fraction, I could start at my x-intercept and then apply my slope of up 2 and right 3. And what you'll notice is that it will end up going through that intercept. My line in this case is solid. The y values are greater than, so my solution is the shading between those two lines. Again, technically the one graphs above the red line, but I don't need to see that if you graph that 1 second. You just need to show me the overlapped solution area. So again, that's what we focused on last week. This week, we're just extending these thoughts one step further by adding in more equations. So what we're going to do today is look at something called linear programming. Linear programming is a way of taking inequalities, but now we are finding their maximums or their minimums. So linear programming is going to create, like we did with our word problems, kind of more triangular regions or regions that are bounded on all ends, where our vertices are going to intersect. where those vertices intersect are going to create minimum or maximum quantities. An objective function is the quantity modeled by linear programming that you want to make as large or as small as possible. So sometimes when we have our linear programming, we're going to also have an additional equation. That equation is typically a profit equation, where maybe you take the minimum or the maximum cost and find the minimum or the maximum profit. Constraints are restrictions on the variable in an objective function. Oftentimes, constraints are domains not being able to be negative. Time can't be negative, so that's a constraint we will see. If we're talking about producing a number of items, you can't produce negative items, so that would be a constraint we might see. And then we have something called a feasible region. That's the points that satisfy the constraints of an objective function, aka the shaded region. So again, if you finish copying down the vocab, you can read the next problem at the top of the next page. That's the problem we're going to be working on. Okay. So it says, suppose you want to buy some tapes and CDs. You can afford as many as 10 tapes or 7 CDs. You want at least 4 CDs with at least 10 hours of recorded music. Each tape holds about 45 minutes of music, and each CD holds about an hour. So let's start with just talking about tapes and CDs. So we will say that X is tapes. And we'll say Y is CDs. And we know that we want at least 10 tapes and a minimum of 4 CDs. So you have 0 less than or equal to X less than or equal to 10. Because again, we cannot buy less than 10 tapes. You cannot buy negative tapes. So tapes has to be greater than 0, but less than 10. And then we want at least 4 CDs. But I can't afford more than 7. So you can have between 4 and 7 CDs. And then we're talking about hours of music. So we have that each CD holds an hour. and each tape holds 45 minutes. So 45 minutes is 3/4 of an hour. So we can say that we have 3/4 x plus 1y. So that if you add the number of tapes and CDs you buy together, their total has to be greater than or equal to 10 hours. So we have that we need at most 10 tapes. So that's this horizontal or vertical line here because X is tapes. And we also know we have the constraint at 0. And then it's all of the shading in between. We know that we are limited to 4 CDs and 10 or 7. So we know that CDs has to live between these two lines. And then our final constraint is the hours needed for music. So we know that we have 4 corners to this. We have corner 1, where I buy all tapes and no CDs. Corner 2, where I buy all CDs and no tapes, where you buy your maximum number of tapes and CDs, etc. So the 4 corners represent the absolute mins and maxes offered. So those are my min and max of my vertices, and then we're going to graph this line right here, which represents the hours of music per device. So this is the same as saying y greater than or equal to negative 3/4 x plus 10. So go ahead, all right, so go ahead and plot that point. So it goes through 0, 10. And then down 3 over 4, down 3 over 4, and y's are greater than, therefore you are shading above. So you have this trapezoid solution region. Then it asks, does each ordered pair below satisfy the system of your graphed equations? So we have 4, 7. So does 4, 7 work? Yes. 4, 7 is actually one of the vertices of my graph. It's up here at the point of intersection. Then you have 12, 7. 12, 7 will not work. I don't even, in my opinion, need to check because I know that my X was maxed out at 10. So a 12 is beyond my 10, so that's a no. 7, 6. That's in my shaded region, so it's a yes. 9, 4. That also works. And 10, 4. That also works. It is another quarter. So then it asks if you buy tapes at $8 and CDs at $12, write an objective function for the total cost. So again, everything in part A, B, and C was part of the linear programming. The objective function is our cost. So it says if you buy tapes at $8, so that means my X value is 8. And then CDs at 12. So that means my Y value is 12. What is your total cost? Well, my total cost would be 8x plus 12y, depending on the number of x's and y's that I purchase. So again, my total cost would depend on the number of x's and y's that I purchase. Those totals come from what we call the Vertex principle of linear programming. So those totals would come from what we call the Vertex principle of linear programming, which is that if there is a max or minimum value of an objective function, it will occur at one or more vertices of the feasible region. So what that means is that the total cost at its min or max will come from one of the four corners of the trapezoid we graphed. The min or max cost will come from one of the four corners of the trapezoid we graphed. So what we want to do is go back and look at our graph and determine what are the vertices of each of those four corners. So we already identified this vertex here to be 4, 7. This vertex is 10, 4. This vertex is 10, 7. And then over here, this is at 1, 2, 3, 4, 5, 6, 7. So it's at 7, 1, 2, 3, 4. So we have 4, 7, 7, 4, 10, 4, and 10, 7. So we have four possible vertices that we need to plug in to our cost equation. 4, 7, 7, 4, 10, 4, and 10, 7. So again, your cost function is C. Sometimes you'll see it written as XY because you need both an X and a Y to get your answer. So you'd have 8 times 4 plus 12 times 7. 8 times 7 plus 12 times 4. 8 times 10 plus 12 times 4, and 8 times 10 plus 12 times 7. Okay, so go ahead and plug those in. So you get 116. 164 and 104. So our max occurs, which makes sense, at that top peak where you buy the total or the max number of tapes and the max number of CDs. Our minimum occurs where we buy more tapes than CDs because tapes are cheaper. Okay. So let's look at one more example for today. So sometimes we don't have word problems. We simply have graphs. So you might be given something that says find the values of x and y that maximize and minimize the function p, where p is equal to negative 5x plus 4y. In the case of this problem, that p function, that is my objective function. So just to help with like vocabulary, that p of x, y function, that is my objective function. These functions here given to me, these represent the constraints. And then what I get when I shade is what we consider the feasible region. So let's go ahead and graph these points to start. So we have the equation y greater than or equal to negative 2/3 x plus 11/3. So not exactly the nicest points if you start with your y-intercept. However, if I start by plugging in 1 for x, you get negative 2/3 plus 11/3. And when you plug that in, negative 2/3 plus 11/3 gives you 9/3. Well, 9/3 is actually 3, because 9 divided by 3 is 3. So instead of trying to start at that awful y-intercept, I can actually start my graph at the point 1, 3. So I looked at the equation and I said, oh, if I plug in the number 1, I could get a prettier point. So that's what I did. So again, instead of starting at the y-intercept, I'm going to start at 1, 3. Now I'm going to apply my slope. My line is solid. And it's y greater than or equal to negative 2/3 x. So that means we are going to shade above. Then I'm going to do something similar for the second line. So I have y less than or equal to 1/4 x plus 11/4. So once again, if I plug in the number 1, 1/4 plus 11/4 gives me 12/4. And 12/4 is the same as 3. So 1, 3 is actually an intercept between these two. So they're both going to meet at 1, 3. That's going to be a vertice of my region. And then this graph goes up 1 and over 4. My line is once again solid. The y values are less than, so we're going to shade below. And then the last equation, this is why there's so much graph down below. The y-intercept is negative 11. It goes up 3 and over 1. My line is solid. And it's shaded above. So my feasible region is that triangular space. There are 3 points of intersection. So my vertices intersect at 1, 3. They intersect right here at 1, 2, 3, 4, 1. And they intersect at 5, 4. So those are my possible points of max or min. So in order to find the min or max, we're going to plug into P those 3 points. And solve. So my max is at 1, 3, and my min is at 4, 1. So for tonight, what I want you to do is turn in that packet. It's after the notes, but there is a linear programming homework day 1. So you're gonna do the linear programming homework day 1. So your packets are a little different this time. They go notes all, and then homework, and then project. So you're doing the linear programming homework day 1. You'll turn it in on Wednesday. Like you'll do today, and then you'll have homework for that tomorrow, and then everything will be due Wednesday. So like if you have questions tonight, you can ask them tomorrow in class.